Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss some specific application areas of nickel based superalloys for gas turbine engine, and we will try to see the chronological order of the development in these specific areas, not only in terms of optimization of processing condition, however, also the microstructure, how it evolves in different processing condition, and the beneficial effect of both processing condition, optimization of the composition, means alloy composition, in order to develop a specific microstructure and the volume fraction of the desired phases. In case of nickel based alloy, you know that the main hardening mechanism comes from two of the mechanisms. One is solid solution strengthening, another one is precipitation hardening. So, here precipitation are the gamma prime phase, that is nickel 3 aluminum. Okay. So, let us start today's discussion. Here in the left hand side, you can see some of the failed high pressure turbine blade, and these blades are joined here with the disc. So, we have basically a disc like this and the blades are mounted on it. This is the specific design of a gas turbine engine. In the right hand side, I show you the same sectional view of a gas turbine engine. This is a specific Rolls-Royce Trent 800 engine. So, the front part of the engine are the compressor, and then there are combustion chamber and then the turbine. So, here these are the turbine which is the high pressure and the low pressure, or in between there are some intermediate pressure turbines, and at the end it is basically the exhaust. Now, here the front part, compressor part, is mostly made of titanium based alloys, and here in the turbine section the nickel based superalloys are the major use of turbines. So, here you see this is also a disc, and on the disc there are blades that are mounted. So, in the left hand side I show you a failed high pressure turbine blade, and you can see that how severe the failure has occurred. So, specifically if you look at these superalloys or nickel based superalloys, two of the major component in a turbine are made, and we need a specific look into it. So, the second part is the turbine disc. Now, before going to the detailed discussion on the turbine disc and the blade, we first need to look at the high temperature creep behavior of the pure nickel. So, in case of nickel, you will have a look, this is a plot with time versus engineering creep strain. If you look at these creep curves, here the primary, secondary and the tertiary, all parts are available at different stress level. So, this is the creep test has been done at a fixed temperature of 371 degrees centigrade, and the stress has been varied to develop these creep curves. Now, the steady state you can see you can achieve for at 147 megapascal at this temperature. Now, if we add a ceramic particle, and we have already discussed that TD nickel, thoria dispersed nickel, means I have a nickel matrix, okay, and I incorporate some thoria particles in it. Okay. So, TD nickel is a very good creep resistance alloy. So, in the right hand side the stress is fixed. However, we try to measure the maximum time to rupture, means until what time the material survive and then it fails. So, the rupture time in case of a higher temperature, let us say something like 725 degree centigrade, you can have a look that it basically gives some failure. So, this is the total creep strain, and here in the x axis this is the time. So, in case of Fourier dispersed particle, you can go up to much higher elevated temperature, and one must look at what are the mechanism involved in such a high creep resistance, because in nickel based superalloy we purposely have chosen nickel, which is a FCC crystal structure, as a matrix. Okay. So, the mechanism mostly involve with the desired steady state creep at a given stress and at a given temperature level. Okay. So, for very common purposes of superalloy development, we apply actually 170 or 72 megapascal stress, and the first generation, second generation, third generation or fourth generation, and this generation of several superalloys has been developed in terms of a higher stress and higher creep life, means time to rupture. So, the steady state creep is one of the very important factor to look into the properties of the nickel based superalloys. So, if we see the fundamental of this steady state creep behavior, that there we basically assume that there are two different components to achieve a steady state creep. It is very simple. So, there is one mode of softening mechanism and there is one mechanism, that is the hardening mechanism. And in case of all the crystalline alloys, we explain the softening mechanism in terms of annihilation, and multiplication is the hardening mechanism by dislocation. So, if one can achieve a steady state creep, it simplifies that net dislocation density in the alloy is almost constant. So, in such a case, there are some recovery controlled stages where when temperature is very high. So, dislocation always try to annihilate and recover the structure. However, recover from what kind of structure? So, at a intermediate temperature level, such kind of polygonized network of dislocation one can see, and interaction with this dislocation with some particle will give you some effective strengthening and better creep life. Now, the recovery control stages, here the temperature is sufficiently high and creep occurred if we think about a pure metal, let us say a pure nickel, such as nickel actually. So, here a combined climb plus glide mechanism is involved, and if gliding dislocation basically pinned, then small amount of climb can release it, allowing further glide to occur. So, let us say a dislocation is gliding on a plane, and climbing means that there are many planes and dislocation is climbing on other planes and trying to find a alternative way, because if dislocation encountered with a particle and if this is a ceramic particle, there is no way to cut the particle and dislocation can go to this side and this process is stopped, then dislocation should find out a alternative path, and this is actually the climb mechanism. Now, in majority of the cases you will find that the creep resistant alloys, we always apply them at a temperature higher than 0.5 Tm, and at 0.5 Tm or higher temperature, the diffusion is very much important process, because below 0.5 Tm the grain boundary diffusion is dominating factor, whereas at above 0.5 Tm the grain body diffusion, or let us say we call it as lattice diffusion, is important. So, now pipe diffusion is also a diffusion, that is basically goes diffusion occur through the grain boundaries. Now, along a dislocation flow. Now, the process is rate controlling the lattice diffusion when we apply a temperature 0.5 Tm, means I am talking about the creep temperature. So, a steady state regime in that case, which is well established by the dislocation cell substructure. Here I have shown you a dislocation cell substructure, whereas this is a core mechanism and the lattice diffusion always allow the dislocation to bypass. And in general, the formation of such kind of subcell and subgrain type of microstructure that arises due to the polygonization or due to the climbing of the edge dislocation, since cross slip become much easy at a higher temperature. A cross slip means dislocation basically bypasses such kind of particles. So, if we think about TD nickel, then we can easily understand now by this total discussion I made so far that why TD nickel is one of the very good creep resistance alloy compared to a pure nickel. Now, if I look at the creep properties of a TD nickel, if we look at the properties of a TD nickel compared to other superalloys, TD nickel, since it has a nickel matrix, and I told you earlier that the dispersion strengthening, here we have thoria particle. So, this is a dispersion strengthened alloy, not precipitation hardened alloy. Precipitation hardened alloys are gamma prime phase. Now, this TD nickel shows a very good creep resistance compared to other nickel based alloys when we have a wide range of temperature of application. Okay. However, the precipitation hardened alloy, the stress for rupture basically decreases when we consider, let us say here this is a schematic for 100 hour of let us say use. So, we can think about for 100 hours of service life, we have to apply TD nickel below let us say 200 megapascal if we go for 700 degree centigrade application and so on. So, so from this plot we understand that a dispersion strengthened alloy sometimes shows us some good properties at high temperature creep. Now, if we look at the very specific application of nickel superalloys for let us say the blade application, with time there is a chronological order of development in terms of process and composition. So, from 1945 onwards the wrought alloys was developed. Wasp alloy was one of the very famous alloys. After that, we find that the conventionally cast alloys was developed, where some of these Mars series was developed, and a typical cast microstructure is a blade is shown here. This is a very common let us say polycrystalline cast alloy, where we will get a equiaxed grain structure, but when we apply stress, the cracking always tend to occur around these grain boundaries. So, that is one of the disadvantage of the equiaxed crystal structure. Whereas, later on the directionally solidified alloys or this is a processing technique where grains are elongated along the direction of the heat extraction. So, let us say this is the heat extraction direction and the grains are also elongated along this direction. So, here you will see that if we apply some stress, the grain boundary amount along the perpendicular direction to the application of the stress is relatively low. And then to apply these superalloy or to develop the superalloys for further higher temperature application. This is let us say the temperature for 1000 hours of creep life. So, single crystal is preferred. Here CMX series is very much famous actually. So, this is a single crystal alloy and this is a finished blade, and you cannot see such kind of structure macroscopically. So, there is a chronological order of development only because we need a higher temperature of application, and then we have seen that the thermal barrier coat was widely applied on these blades. Now, let us think about what are the processing condition, why we really preferred for such kind of technique of producing these blades. So, for producing blades, the investment casting is one of the very well known technique. Here we make a investment slurry and we produce the mold, and then we pour the liquid into that portion in the mold cavity. So, in case of pouring, if we need to grow along a particular heat extraction direction, then Bridgman type of technique, which is a slowly removal of a mold inside a heat source. So, here this is let us say a motion of the mold along the bottom direction, where the furnace is fixed or otherwise, means we can move the furnace on the top side. Now, you can see that this bottom part, which is a water cooled chill. So, the solidification will begin in this portion first, and now the grains will grow. Now, you can always ask why the grains are growing only this direction. Yes, the grain or the dendrite also form along this direction, but the growth rate, means the velocity of the growth is higher along this direction. So, the growth of a inclined dendrite will always be suppressed. So, we can always get a elongated grain and slowly we remove, and this is let us say a solidification front, where we have liquid and we have liquid here and we have solid here. So, this is the interface. So, we slowly drag this mold down in order to preferably produce this directional solidification. But few seconds ago I just said that the single crystal blades are mostly important and it resists a much higher temperature, and therefore, we can adopt very similar technique. However, we need to adopt a crystal selector at the bottom part of the mold actually. What we do here, we have a starter and then we use a crystal selector. What it does actually, it mechanically block the grain. How? So, let us say this is the starter block and the grains are growing along the heat extraction direction. So, they all are growing. Now, they have grown, and here let us say I have a liquid, and then I preferentially allow and drag this mold downside. So, there is a interface of liquid and solid, let us assume. So, these are the grain boundaries and they are blocked here, where this is a grain boundary which went up to here, but this is also a grain boundary which went up to here, but ultimately you will see that only this grain have a chance to grow. So, this is the only grain that has a chance to grow. Now, it grows and then it enters into the mold cavity. So, we start with a single grain which fill up the whole mold cavity in order to produce this single crystal blade. This is very interesting phenomena, and there are many different type of helical type of shape or this type, and let us say conical type of shape, there are many shapes, and this is a directly cast solidified blade with such kind of helical crystal selector. Okay. Now, we need to go for various technique and final heat treatment, so that we can get basically the finished blade which looks like actually such a image. And if you look at a microstructure, then you will see such kind of dendritic microstructure, and after proper treatment or heat treatment, we will have such a microstructure with gamma prime phase. This is a single crystal which CMX4 and gamma prime phase in a this kind of dark region is the nickel matrix. So, we understood that the processing condition itself is very much essential on developing these blade nickel superalloys. Now, with time there are many compositional changes, and let us say the processing technique has been evolved, which I just discussed few minutes ago, and here I show you one of the compositional changes that occur with the time. So, we already know that there are specific element used for specific purpose. For surface protection we use aluminum, chromium. However, for solid solution strengthening we basically use molybdenum, tantalum, tungsten and rhenium, and grain boundary strengthening we use let us say boron and boride and carbide and this. So, aluminum is preferentially added also for precipitation strengthening of the gamma prime phase. With time you will see that the aluminum content is increasing. So, this was a conventionally cast, which was a very old technique, and then the blades with first, second, third, fourth, even today there are 6 generation blades. And so, the aluminum concentration is increasing. There are two purpose of this aluminum, one is the surface protection, but we preferentially like that addition and increase of the gamma prime volume fraction. Now, you can have a look that the cobalt content and chromium content they also decreases, and because we need to apply for higher temperature. So, chromium oxide does not provide proper protection. However, the molybdenum and tantalum they are also used, but tantalum and tungsten which is used a lot these days, and the specific purpose is basically to have a better solid solution strengthening as well as the creep life. And similar way the rhenium is also used for this kind of better creep life. Now, there is another element that has been added and the percentage is increasing. There are some specific purpose, it is called ruthenium. The ruthenium basically suppress the dendritic segregation, means the alloy preferably try to segregate in the interdendritic region, and it should require hindering of the topologically close back phases. And the effect you can see very clearly that if we have time to rupture and creep strain, then conventionally cast alloy does not perform well as the single crystal blade. So, single crystal is always better in and gives us a larger time to rupture, and it require higher creep strain, and so the single crystal blades are always preferred if you just have a look at these plots. Now, if we think about some of the composition, microstructure and properties of these superalloys, the volume fraction of gamma phase should be higher like 70%, and the portion of gamma prime forming element that should be high. So, there are some design considerations. So, I am just talking about the design consideration. However, the misfit should be small, so that we will get effective strengthening. Now, the creep strengthening element like molybdenum, tantalum, ruthenium that I just said, and avoid the precipitation of topologically close back phases should be considered. On the other hand, the surface degradation like exposure to a hot and a very aggressive environment should also be considered. So, these are the 4 design consideration that one must think about. Now, I show you a simple example of a weight change, means the corrosion rate or high temperature oxidation rate in case of a single crystal superalloy. Here you see there is a large chance of a oxidation and there is a high rate of weight loss. This is a negative side. So, weight is losing this side. However, if we specifically add very small amount of yttrium, lanthanum or let us say some rare earth cerium, then we will increase their creep life. So, the oxidation temperature here was 1093 degree centigrade. So, we must consider some of these design criteria to select what are the alloy composition one must look at, and it is for sure that if we think about a good grain boundary strengthening, then if there is no carbide and boride, then we will get definitely a creep life which is good when the mismatch angle is less. So, less than 5 degree mismatch angle is always preferable, but we can still increase it when we have some controlled grain boundary strengthening. So, the grain boundary strengthening means that I have some grains and then I introduce some carbides or borides. This is always preferred microstructure for a better creep life. Now, for a disc application, we should have a look at the different processing technique. For disc, to make a disc, we have to go for some particular shape which appear like this. This is a section. Okay. So, we start with a vacuum induction melting, then we go for some electroslag refining process, so that we remove some of the slag and make a more pure alloy. Then we go for some vacuum arc remelting, so that any kind of dissolved gases to be came out. After that we go for some heat treatment. So, after this process we come here and then we simply offset and draw it and then we basically forge it. This is a very conventional production process using ingot metallurgy, which I have discussed for making a such kind of disc. However, please have a look that a 95 kg we have to start with in order to achieve 5 kg of the product. Okay. So, there are some alternative technique that is called hot isostatic pressing, means this is a powder metallurgy processed 33 kg size metal, and then we simply give some pressing, so that we get this final product. On the other hand, we can also go for some direct hot isostatic pressing in order to achieve this product. However, since these are the forged product, you can easily understand that they are not at all single crystal. So, these are the polycrystalline alloys. Now, here too we have some design considerations. So, design consideration include that the volume fraction of the gamma prime phase should be 40 to 50%. Okay. So, that we optimize the strength and the fatigue resistance. So, gamma prime forming elements means these aluminum, titanium and tantalum, and we should go for some proper heat treatment, so that uniform distribution of gamma prime particles should be here. These are like this is a schematic microstructure where you can see that there is the uniform distribution, and these are the grain boundaries. Okay. And this gamma prime phase may also appear in the grain boundary region, and these are called the primary gamma prime. When it appears, it basically appears not during solution treatment, but simply is coming from during basically solidification itself. However, there are some secondary gamma prime which basically form at higher temperature during cooling from the solution treatment. So, inside if we make some solution treatment and then cool it down, we can get actually this secondary gamma prime phase. However, this gamma prime precipitate at low temperature during cooling from the solution treatment has a much smaller length scale from 5 to 10 nanometer size. So, after quenching and after aging treatment, we can get 5 to 10 nanometer size particle. This gives a very beautiful and effective strengthening. Okay. So, so you can see that there are so many different types of gamma prime phase that form in different length scale from 1 to 10 micrometer, from 72 to 120 micrometer and to 5 to 10 nanometer size. On the other hand, to optimize the properties, we need a grain size of these matrix and let us say the grain size of this precipitate properly. So, 30 to 50 micrometer grain size is always preferred for this purpose. On the other hand, small quantities of grain boundary elements like boron, carbon, they could be beneficial for a better creep and low cycle fatigue life. So, with this we finish today's discussion and we will further discuss other different types of superalloys in the next class. Thank you.